So, all right. When we talked last time on Tuesday, I went through a function and I just made up a function that said A, B, or not C, and it was different. This is different than the one I did on Tuesday. Just simply to go through the process again, right there. And typically, when we want to solve this circuit's going to look like this, right here, A, B, and then we go through an inverter through C, and here's my OR gate right there, X right there. Now this is typically called sum of products notation, right there. So, and we'll see why it's called that. We really haven't gone into the rules of Boolean algebra. I'm just going through how we go from a circuit to that there. And normally if you follow some books, and the easiest way to look at this is I'm going to erase this X here, and I'm going to put the term AB here, and then you can also put the term C naught there, and solve the intermediate ones first. That's there, and then we finally look at X, right there. So we go through here, and we put in our inputs, and I know this is the tedious part here. One of these days I'm going to actually just have this as a template. I just tap that there and it shows up automatically. And in some ways you could do this with an Excel spreadsheet easier than a piece of paper if you're going to do this at work. Unfortunately, you can't use an Excel spreadsheet when you take the final exam or quizzes, so we may as well do it on paper here, right there. So 1 0 1 1 0. Excuse me, I got that one. Yeah, that's right. And then 1 1 1 1 2 3 4 5 6 7 8. Okay, that's my checking point to make sure I didn't miss anything. There should be 8 of these. So as we go through and we fill in our first table, right there, this is only going to be a 1 here and here, right? A and B can only be a 1 in those two spots because we're looking at these two columns here. Every place else in that list there, A and B are when we add the two of those, it's going to be a 0. So we go ahead and put zeros into that there. And then we do the not C. And the not C is basically going to be this column inverted, right there. So this is going to be 1 0 1 0 1 0 1 0. Okay. Now X is going to be any place, and it looks like when I use that yellow, it's hard to see, isn't it? On my computer, that yellow doesn't line it out, but I'm just going to put a yellow mark here, or excuse me, a yellow mark here and here, because we're going to look at those two tables, columns right there, and we're going to solve for this expression right here, right there. So if either of these two columns here is high, the output is going to be high. So here, this is a 1, here it's going to be a 0, here it's going to be a 1, here it's going to be a 0, here it's going to be a 1, here it's going to be a 0, here it's going to be a 1, and here it's going to be a 1. So that's the output of this function right there. So it's fairly straightforward. You do that. On Tuesday I went through the Quartus software where I showed how you would do that. And before I get too far, let me make a quick announcement. We don't have our class is scheduled outside of a lab, all of our classes, right? You know, it's this room and the other room is 3:30? I can't remember which our other room is. I think it's 3:30 up there. When I do have lab days, and I will be scheduling lab times, one of the two, I don't care which one it is, you know, whenever I can get the room upstairs. The lab will be in room 414 up on the 4th floor is where the lab will be when I schedule lab days. On lab days, I have a very mean streak, and that is that once I start the briefing for the lab, I lock the door. And it's not that I'm a real pain in the neck on attendance. Because I record 90% of the lectures. You know, if you show up late, I don't really get uptight about that. You know, in most Western cultures, it's considered rude to show up late for classes, but people do anyway from time to time. But on lab days, I will start the briefing for the lab, and especially the first few labs, and probably most of the labs, I will go through on how to do the lab up there, and then you do the lab after I go through the demonstration. If you miss the demonstration on the lab, then I have to do it over again. So when I got people coming in, let's say I do a lab on a Thursday morning, and I can't remember when our other session is. Our other session is we meet Tuesday. Our other session is in the afternoon, 3 o'clock. Let's say if I do it on Tuesday at 3 o'clock, that means you need to be there at 3 o'clock. If I do it at 10 o'clock or 10:15, you need to be here on those days. Other days, I'm not so particular. Right there. So I'm just kind of warning you ahead of time. That's there. So 3 o'clock shouldn't be a problem. 10:15 shouldn't be a problem to be here on time. I ran into the problem with one of my other classes that the second one was at 5 o'clock, and everyone had a class that ran from 3 o'clock till 4:45 or whatever time it ran to, and they only had 15 minutes to get from between classes. So getting there at 5 o'clock was a problem for Asr prayers. With you, that shouldn't be a problem. So I moved that one to 5:15 to give people time to pray Asr. But for this group here, there's no reason to move it because there's no prayers before 10:15 other than Subu, which is at 6, right? Get there. So, and then of course, Zohar is at 1:30, so there shouldn't be any problems. If there is a problem, let me know on the Thursday. If someone happens to be scheduled for a, let's see, our other one is Tuesday. If someone happens to be scheduled for one, say 1:15 or 1 o'clock to 3 o'clock, that they're where you need to pray Zohar before that, let me know, and then I'll move that one to 3:15 on those dates up there. So I just, it's just the problem is that if I get into the lecture, because I locked a bunch of people out last Monday at 5 o'clock, about 5:10 I went over and locked the door, and I had like 7 people come in and they were late because of prayer. So I just want to give you that warning now, and I'll try to remember it later. Okay, but this is basically the way that you would do this. Now let me go the other way, and let's go through and look at a circuit and see how we would come up with the truth table from the circuit right there. And really, to come up with the truth table from the circuit, it's pretty much the same type of method, only what we do is we write the equation from the circuit. So if I put a circuit down, let's just put a circuit looks like this here, and I'm going to call this A, let's put an inverter in here, B, let's bring B here, and then C. Something looks like this right here, right there. When we look at this particular circuit here, our equation, we would look at the circuit, come up with our equation. This point right here is A, B naught right there. And I get that by looking at the 2 inputs. This was an inverted. This one is BC right there. So that's by circuit that right there. So my output X is equal to A, B naught, or B, C right there. That's the equation from the circuit. Now, if we're going to do the truth table, we would do the same thing. We would do A, B, C right here. And you would think that I would get tired of writing ones and zeros. Actually, at some point, we'll quit writing so many ones and zeros, but right there. And now, it's really the same process. that there, once we do this, we're going to go ahead and put a table here, A, B naught, another column here for BC, right there, and then another column over here for, and I'm just going to say X, and underneath there I'm going to write AB naught, if I can write that small, for BC, right there. Actually, what I can do, nope, it won't let me write it bigger, right there. Okay, so we go through there, and we just look at this. This, any place A is a 0, I can go ahead and put a 0 in here, right? You know, just do it quickly. And then we look at the rest of this, and whenever B is a 0, we can put a 1 here. Right there. So that's that column there. So, does that make sense what I've done for this column there? Then the next one is BC. So every place B is a 0, we can go ahead and write a 0 here. Right there. There should be 4 of those. And then we look, if C is a 1, then we can go ahead, that there. So in this particular case, B is a 1, C is a, so C has to be a 1 and B has to be a 1 to write this here. So actually we can look here, this is a 1, this is a 0, because I'm looking at C, C is a 0. Here it's a 1, right here, because we're looking at these two columns right here, and these are zeros right here. So once we have that there, then we look at these two columns, and if either of those is a 1, then the output is going to be 1. 0, 0, 0, 1, 0, 0, 0, 1. So that's our function right there. Right there. So it's a fairly straightforward process going between one and the other. Now, the next thing we're going to be looking at is we're going to start trying to write simpler equations in order to reduce the number of gates. So at this point, I'm going to revert back to the book a little bit, just so that I don't forget all the rules. So what we've covered thus far, just a quick review, is we've gone through definition of what digital is versus analog. We talked a little bit about that theory from chapter 1, and I've been using the Floyd book here for this. And then we went through numbering systems. We went through the basic gates, and, or, not, and XOR, right there. And we've gone through how we go from the equation, how we develop the equation from the circuit, and how we go from a circuit to an equation, and how to generate what's called the truth table, right there. So what we're going to be going through next is the rules of Boolean algebra on how to simplify these circuits. Now, when we simplify the circuits, we will always work from the equation, and later on from the truth table. We won't work with the circuits. Right there. We don't try to simplify the circuits by looking at the circuits. We look at the equation and we apply the rules of Boolean algebra. These are all in the book, and I'm going to refer back to the book simply so that I follow the same order and I don't miss one right there. So let me go back to the book here, right here, and everyone has this book here, and see, and if you look at the book, they've got some really, there's a nice, neatly, a long, drawn-out circuit there. You can see that they can get messier yet, up there. But again, they go through the same type of thing. Actually, this is full sum of products terminology right here. Where am I? Right there. So, okay, all right. Since I'm following the book, let me go ahead and cover this topic here out of the book too. Right there. One of the things we could do if we want to write our equations very quickly from a truth table, right there, is we can write it immediately from the sum of products notation. Right there. If I'm given a truth table, and I'm going to put across the top here A, B, C, and X, and I spent half the class time writing these tables, don't I? That's there. Okay, and we look at our output, and I'm just going to put random ones and zeros down. That's there. I'm just saying this is any truth table that you're given and you're asked to come up with a circuit for. That's there. The easiest way, and that there, is I'm going to write 1, 1, 0, 1, 1, 0, 0 right there. And when I do that, I'm going to just put little marks here. Every place there's a 1, I will write a term for that. And the term is going to be basically, I'm going to look at this, and if there's a 0, it's going to be A naught, B naught, C is that term right there. And what I'm going to do here in a minute is I'm going to write all the terms down in another table. This term here is going to be A naught, B, C naught. Now what we're looking at here is if this is a 0 here, I write A naught. If this is a 0, I write B naught. This is not a 0, that's a 1, I write C. Right there. And what that is telling me that if I have an AND gate right here, that A has to be a 0, B has to be a 0, and C has to be a 1. So we put an inverter on each of these right there for this to be true right there. You know, as far as our input goes. We don't put the inverter there, but we write that as A naught right there, essentially. In order for this to be true, we actually would put an inverter in the circuit, actually. We would actually put the inverter in the circuit. So we would draw this circuit as this right here. This goes into the AND gate, and this is the term A naught, B naught, C right there. Right there. So in that particular case, every place there's a 1 here, this would be A, B naught, C naught, and this would be A, B naught, C right there. So whenever any of those inputs are 1, the output of any of those gates are a 1, then my output is going to be, I want my output to be 1. So I would then basically write my expression as A naught, B naught, C, or A naught, B, C naught, or A, B naught, C naught, or A, B naught, C equals X. So I can very quickly write from a truth table an expression for this. This is probably not the most effective way of doing it, but it's one way of doing it. Right there. You know, my next step is to do what I'm going to be talking about next is simplifying this circuit. Right there. So let me just kind of go ahead and put a table up here. Right there. And this table is just going to look like this: A, B, C, right here. And over here, I'm going to put what the gate you would use, that there, the term you would use for that particular, up there, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Trust me, it's just as boring to sit here and write these ones and zeros as it is to watch me write them. That's there. But unfortunately, that's the only way to explain this material. Right there. So as we go through here and we write these terms, right there, this term is A naught, B naught, C naught. This term is A naught, B, C naught. This term is A naught, B, C naught. A naught, B, C, A, B naught, C naught, right, yeah, that's right. A, B naught, C, A, B, C naught, A, B, C, right there. And sometimes people will use the term, they'll call these the mini terms, and they'll refer to this as 0, and this should not have a knot on it, but that should be just a C right there. That's a mistake right there. Right there. This is 1. This should have the knot. It's hard to see with my handwriting. C knot. This is term 2, 3, 4, 5, 6, 7. Sometimes some people will say that X is equal to and they may say 1, 3, 5, and 7, and that's the same thing as saying X is equal to A naught, B naught, C plus, and I'm not going to write the whole thing, but you can see how, as a way of simplifying the writing that's there. I won't get into that. I don't know if this book uses that particular terminology or not. I haven't memorized this particular book. To be honest, I've taught digital out about 4 different books over the years, and they all cover things a little bit differently. I'm trying to stick to the Floyd book for the most part right now. I may go back to the Tochi book. So I'm using 2 books for this class. In the U.S., I would never use 2 books because I wouldn't make people buy 2 books. But since you have the 2 books, we can go back and forth. And in your case, I suggest that you look at both books as you're studying because they explain it differently in different English terms, different ways of explaining it. Since English is a second language, seeing it explained 3 different ways, my explanation in the 2 books explanations will probably help you than just seeing one reference right there. So, okay, that's a way of quickly writing a function from the truth table. Up there. Now I want to jump back to that there and get into Boolean algebra right here. And this gets into more of the same discussion. This actually shows a way of how you would draw that expression for a 4 input right there. And if you look at this here, they've got DCBA here, and then they run through converters. And each one of these AND gates is connected to 4 inputs right there. So this happens, right there. So this is a way that you could do that. To be honest, if you use a programmable logic like we'll be using, you could just do it this way and the software will simplify the circuit for you. That's there. But we're going to go through determine if it can be simplified right there. Now, hopefully I can find our rules, and it looks like I've gone, it may be back in chapter 4. I may have to go back to chapter 4 here. Give me a second. Your combination logic analysis. Yep, it's chapter 4 because there's our Karnoff maps. Okay. Right here, let me just jump in here. Karnoff maps. We'll get to that later. And sometimes, group table. There should be a nice little table here somewhere. Standard forms of expressions. Simplify. Okay. I want to find the table of the Morgan's rule. We're getting close to it here. All right. Okay. This is what I was looking for. Sorry for not at there. This is our table of Boolean rules right there. So, and you basically will end up putting this to memory. Let me just go through these one at a time from the table, and then we'll use those as a way of simplifying the circuit right there. The first one basically says that if I OR anything with a 0, it's going to be the same thing right there. And remember what that says in terms of circuits there is that is if I have a circuit and an OR gate, and one of these inputs is a 0, and this input is an A, the output is always going to be A, right there. Now that by itself doesn't necessarily make our circuit simpler, but when we look at some of the other rules, it will make things simpler right here, right there. So as we go back to, all else fails, go back to here. The next one says that if I AND anything with a 1, or anything with a 1, the output is going to be 1. We don't care what A is. If we use the OR function with A, and we're ORing it with something we know is a 1, the output is always going to be 1. And that goes back to the definition of the OR function. If either of the two inputs, if any of the inputs are 1, the output is going to be a 1. Now the reverse is true with the AND. If we have a 0 in there and we're ANDing it, the output is always going to be a 0. And that goes back to the definition of an ANDing. All inputs have to be high for the output to be high. Right there. So if we AND anything with a 1, the output is 1. Right there. Now if we OR something with itself, the output is going to be itself. Right there. If we AND something with its complement, if we OR something with its complement, A plus A naught, we're going to get out a 1. That one's not quite as obvious, but if you think about it, if A is equal to 0, then A naught, right there, then that tells you that A naught is equal to 1, right? If A is equal to 1, A naught is equal to 0. Well, if we're using the OR function, A or A naught, one of them is going to be a 1. So if we OR A and A naught, the output is always going to be a 1. The next one is the AND function that basically says that if we AND A and A, is going to be equal to A. Right there. Now this one here follows the same logic as the one I just talked about with the OR function, that A and A naught is always going to be 0. Because A and A naught both can't be 1. One has to be 1 or has to be a 0 and 1 is a 1. This here is a double complement. That says that if I take A and I run through an inverter and I take it and run it through another inverter, I get A back. And this is A naught right there. Equals A naught right there. Now sometimes we do this in real life because the reason we do that is we want to add the propagation delays. Now later on we're going to be talking about edge detectors, and we'll use 3 or 4 inverters in order to create a glitch that we use for a clock detector. Right now we're not to that point. Okay. Now this one here isn't quite as obvious right there. And what this comes back to is we've got and they haven't talked really so much about the rules of association and that they're and what's that, community, that they're where you can move back and forth. That's probably talked a little bit. Okay, this is earlier on. Okay, I didn't go back far enough right there. I'll go ahead and cover those 2 rules real quick. I'm sorry. Before I get into this rule right here, let me go back and cover 2 more that I skipped. Right there. For some reason I thought this table was complete, but it's not. That's there. They covered 2 more before they got to that one. That's there. The first rule simply says that A plus B is equal to B plus A. Right there. That there. A times B is equal to B times A. And I'm using the and in plus here. That's the Boolean and in plus, not the algebraic math and in plus. It's the logic and in plus. Now the other one is A B plus C is equal to AB plus AC right there. And that's why the multiplication and the plus symbols start making a little bit of sense why we use them when we look at some of these rules here. And the same token, A plus B times A plus C is going to be equal to AA plus AC plus AB. Right, excuse me, yeah. Actually, if we follow, there should be 4 terms right there, and plus BC, right there. You know, just like you do in normal math, you know, if you have something like 3x plus 4 times 2x plus 5, that's equal to 6x squared, right? Plus, that's a 5, I said, right? So that's going to be 15x right there, plus 8x plus 20, something like that, and you can combine those two, right? You remember doing some of that stuff in basic algebra. Right there. The same basic rule applies here, right there. And if I've got the term A plus AC, I can write that as A1 plus C. Right there. This term, I can say A times 1 right there. That one's a little trickier to see right there. So when I write that, this becomes A plus C right there. So this second A drops out. This is what that expression does there. Again, that was a little trickier to see, and the trick to that one is realizing that A is equal to 1 times A, right there. So we could factor out that 1, that there. When we factor out that 1, this becomes 1 plus C, and remember 1 plus C is equal to 1, right? So this term drops out, and that's where we start applying these rules of Boolean algebra, right there. So I'll go back to the book, make sure we've got there. And that's where this comes out here. This is going to be A1 plus B right there. 1 plus B, going back to this term right here, 1 plus B is equal to 1, and then 1 times A is equal to A, so it just becomes A right there. It's a way of that we simplify this right there. So let me just kind of write that a little clearer. So some of you will probably look at this on the video again and go, what was he talking about? This is A, and I'm factoring out an A, 1 plus B, right there. So the term 1 plus B equals 1 using this term right, this rule right there. So the next one is not so clear. That's there. And I just simply say just use it as it is. Right there. You could go through and derive that, and if you went through the book, they probably just use the truth table to prove it's valid. If they're going through algebra to try to prove that, you end up with a mess. But this one here is one that a lot of people don't necessarily see forget about, is this one right here, and that is A plus A naught B is equal to just A plus B. And trying to factor that down, there's some tricks to it, and it's not worth trying to go through it. You just remember that particular rule right there. And then the last one right here, A plus B and A plus C, comes back to that there. And that one we can get, and I'm going to just jump over here and go through the steps to get to that one right there. And that was A plus B times, what was it, A plus C, right? Right there. So when we write that, that becomes AA, right there, plus AC, plus AB, plus BC, right there. Now, what I do to simplify this is I take all three of these terms and factor in A. So this becomes A times 1 plus C plus B, right? Plus BC. This has got a 1 in it, so this whole thing goes away. So we're left with A plus BC, right there. So again, it's very much like regular algebra, but it's got some funny rules right there. Because in regular algebra, AA is equal to A squared, right? In this case, AA is equal to A, right there. So the rules are a little bit different. They get a little confusing right there. You know, A plus 1 equals 1 is not true in algebra, regular algebra. That's there. You know, A times 0 equals 0 is true in regular algebra. So some of the rules are the same as algebra, some of them are different. That's there. So, and that's why some people find digital confusing, is because we're using some of the laws of algebra that you remember ever since, in the U.S. I would say secondary school, but wherever you had your introduction to algebra, you learn all the basic rules in algebra, and now we're changing some of them. So you spent 10 years learning one way of doing this, and now all of a sudden we're rewriting some of the rules. That's it. So it gets a little bit interesting. So let me go back to our book here and go through that there. Again, this is in this particular book, as you can see, they go through all the examples that there. So they go into more detail than I'm going to go into. But there, so they show the gate equivalent for each one of these right there. Right there. So in other words, they say A plus A is equal to A, and they show the example. If A is 0, the output's going to be 0. If A is 1, the output's 1. So you can ignore A plus 1. It's not 2A right there. A plus A naught, they show the example that I showed a few minutes ago. A times A, they show here again, A is equal to 1, that both inputs are 1, the output has got to be 1. If A is 0, then the output has to be 0. So this is on page 188 in the Floyd book, right there. And they go through all these right there. This one here is one that they can prove by applying the distributive law, Rule 2 and Rule 4. They go through the steps as I did. So again, I went through it right there, but everything that I did comes back to here. Here's the one that I said is the confusing one, and you can see the number of steps that it involves in order to prove that that's true. A plus A naught B is equal to that there. And what they're doing here is they're expanding this out right there. So, and they're using this rule right here to say that and it's not quite as obvious that there, but this one here I just remember. I don't go through the proof on that one. So those are the basic rules right there. And this is the one that I just went through right there. So we go through here, and Rule 12, this is just here they're going through with the truth table to verify it. And you can go through that there. So again, we've got the associative and the distributive laws that we talked about a few minutes ago there. So let me go through, and I'm going to kind of break away, and I'm going to cheat, and I'm going to go to the problems at the end of the chapter and pick several of those and work through those so that you can see how these are done. In the textbook, he doesn't show how, he doesn't have any examples. So I want to work a few examples that's there. So, and that's probably going to be all I'm going to cover today by the time I do 3 or 4 examples, because I'm going to do De Morgan. One of the reasons I have shorter classes than some of the other instructors is I've learned after 30 years that I only want to cover one topic typically in a lecture. So if I go through all these Boolean rules and laws and do several examples, I don't want to do De Morgan's because it's a completely different swing in direction. And I just discovered that students' minds can absorb one thing. As soon as I give two major topics to one lecture, you tend to forget which one's which. So let's go to the end of the chapter here, and it's a fairly long chapter, so we're going to spend right there. Okay, well, again, we can use this one right here. Well, this one uses De Morgan's. I don't want to use De Morgan's yet. Right there. Right there. And let me just jump to as you can see, this chapter is fairly long. This is actually one of the longer chapters in the book. So, summary. Okay. Right there. This is still the summary right there. Okay. Evaluate that there. Okay. I'm going, you know what? It appears that you have to use De Morgan's in order to do any of these examples. All right, let me go ahead and talk about De Morgan's. That's fine. Let's go ahead and bring up De Morgan's. That's there. All right, De Morgan's rule is that there, and then simply the organization of the book. That basically says that A, B as a function not there is equal to A not or B right there. A plus B as a group is equal to A not B not right there. That's called De Morgan's rule right there. And it's a little bit of a tricky one that there is that one of the things that's not specified, but A, B is not equal to A not B right there. This is a NAND gate right there. This is a AND gate with the inputs inverted. Right there. So this is the same thing as showing a NAND gate right here. This is the same thing as showing an AND gate with inverters on the input right there. Right there. So when we look at that right there, this is the same thing as showing a NOR gate right there. This is the same thing as showing an OR gate with bubbles there. They're not the same thing. Now, keep in mind that if I put a bubble on this here, that now becomes an OR gate. So you'll sometimes see if I put a bubble on here, that becomes an AND gate. And later on we'll see that is that this here equals this here, and this here equals this here, right there. And later on when we talk about universality of gates, we'll see this will come to play. Right now, you don't necessarily have to remember this, but we will come back to that there. We will have to come back to that. And so De Morgan's rule, and it's just simply a matter that all of his examples have De Morgan's rule used. That's why I went ahead and just brought it up. I was going to leave it go, but now I went ahead and discussed it. It doesn't add a lot to it, but it does add one more set of rules that we need to keep in mind right there. If we see if we see this term right there. So going back to my examples that I have here, find the value of x for all possible variables right here. That there, section 1, if you look at the homework, basically just to evaluate this here, what this is trying to tell you right here is that's just simply, in other words, say, write the truth table, is what that problem's actually saying right there. So as you look at these homework problems, and I steal exam questions out of homework problems, that there, and when I get closer to the exam, I'll be more specific where to look. But as you go through that there, find the values that meet, right there. So as we look at rules and laws right here, let's start off right here, identify, let's just look at here, these are basically identifying the rules right there. What I want to do is simplification. This is really where I want to be right here, is I want to go through these examples here, right there. So I'm going to go through these particular 4 problems here. So let me cheat. And when I say cheat, means I'm going to copy that and that there. Okay. My cheating means I didn't want to redraw it, rewrite them. So I just want to cut and paste from the textbook that there. And let me just kind of go through each of these that there. The first one is A plus B, that is equal to AA plus AB is equal to A plus AB, right? And then I factor out the A again, that's A, 1 plus B equals A, right there. So this is A. B is A naught plus AB. Now you can do this one different ways. One way of doing this is to go ahead, and it's my most common way of doing it, is to go through and just multiply everything out. So I'm left with A naught plus B, right? Right there. A times A naught is equal to what? 0, right? Plus AB. I factored the A and B together. 0 plus anything is equal to that there, so this is going to be equal to AB right there. And I think you can see the value of going through these examples that you can go through and see where they're used. The next one is okay. Stealing pens and pencils. All right. I thought you had a question there. So is everyone clear how these ones are solved? Right there. The next one is going to be C, and I'm going to go through a couple of these here. B, C plus B not C. That's equal to, and again, I'm going to factor out a C in this case. B plus B naught, right there. I factor the C out, right there. So B plus B naught is equal to what? 1, correct? So this is equal to 1, so it's C times 1, which is equal to C. B just disappears completely out of this expression. Right there. The next one is A times A plus not B. D is A plus A not B. A not B. Right there. Again, you can factor this out multiple ways. but the easiest way that I see to doing this, and it's like regular algebra, you practice what that there. That's equal to AA, and that's an automobile association or Alcoholics Anonymous, just AA right there, plus A naught B. Now when you look at this term A naught B, that goes to 0, right? Yeah, so that goes to 0, and AA becomes that there, so it's just equal to A. The other way you could do that is you could take this expression and apply that one rule that I said I always forget. That there. But you'll end up with A when you do it that way. Again, my simplest way is I multiply everything out and then I start combining. And then D is A plus A not B. No, that's one I just did. E is this one here is the next one right there, and I'm going to move it over here. I'm going to solve it over here. A B naught C plus A naught B C plus A naught B naught C. And I'm going to go through and start solving that there. Now the easiest thing to do is start factoring things and see whether or not they fall there. So if I factor, for example, the C out of the first two right there, I'm left with C A B naught plus A naught B right there. Does that help me any? Right there. I don't see anything that's going to help me on that one there. So let's look at the next one there. So that doesn't help me any. And I may draw a blank on here. Sometimes I end up with a. I can factor C out of all these. Excuse me. C B naught C. Excuse me. Now I'm reaching the point that I'm struggling here. A B naught plus A naught B plus A naught B naught right there. Now let's see if we can combine two of those terms to make something disappear. And it looks like we do here. If I combine these two terms right here, this is by far the most difficult one here because it's trial and error a little bit here. If we factor these two, that's going to be A naught B plus B naught, right? So this disappears, right? A plus B naught, or B plus B naught is equal to 1 times A naught is A naught. So now I'm here to, let's just write the whole thing again. A B naught plus A naught right there. And that's probably where it's going to lead, maybe where it's left right there. Not really, because that goes back to that mystery rule. And that mystery rule is a little tricky on this one because that mystery rule has a counterpart to it. This one's tricky and there. And the reason it's tricky, let me go back to the book here, or let me go back to my previous slides there. And nope. Okay, it goes back to, and where am I at here? I know I have the slide here somewhere. Nor. Should be the one right before the De Morgans, but nope. All right. Okay, I'm going to have to go, this is the page we're looking at. Let me go back to the book and find my table in the book here. I wish this software allowed me to put in bookmarks right there. Oh, this is the slide I want. All right. This expression right here, this is the one I want here. Let me grab this and talk about this here. Right here. New. Okay, let me grab this one here, and I want to talk about this one a second here. Right there. Right there, page. Let me go back to one where we were at here. With this one here. Okay. Let me talk a little bit about this one here, and we'll come back to right here. This rule right here that says A plus A not B is equal to AB. Right there. Now, we can reverse those two, and we can write this as saying A not plus A B right there. In other words, we reverse those two, and that, in other words, all I'm doing is inverting that. That is going to be the same thing as A not or B right there. Or we can rewrite it and say A plus A not B not is equal to A plus B not. That's the same rule. By inverting this here, and I could do that by creating a new variable. In this case, I could say C is equal to A naught, and then write the rule as saying C plus C naught times B is equal to C plus B, right? Again, I'm just doing substitution and using the same rule right there. So when we look at this rule here, you see there's three different forms of this rule right there. The book only mentions this rule here, but we can expand this rule by understanding that A plus A naught B is the same thing as A naught plus AB is equal to A naught plus B, or A plus A naught B naught is the same thing as A plus B naught. That's a very tricky rule, and I don't think that you would probably pick that up on without really practicing through it. And the book doesn't cover that, but this same rule has three versions of it. I can derive from this rule all three versions of this rule right there. So going back to my problem here that we had, we've got this expression right here, which is A naught plus A B naught right there. And that doesn't look like this right here because of the B right here. And this A naught is reversed right there. But that's the same, will equate to here, in this particular case, if we apply this rule, we've got A naught where A is over here. We got B naught where B is here. We got A here where A naught is. So if we look at this particular rule like it is here, this is going to be equal to A naught plus B naught. I didn't show that version of it. There's actually a fourth version of that right there. But you have to manipulate this rule here in order to simplify that right there. So then if we do that, we're left with the answer then is going to be equal to A naught C plus B naught C, and we could leave it in the form C A naught plus B naught right there. We can leave it at there. But that's the simplification of that one there. And I should point out, as we look at these homework problems, usually the last one is the tricky one, which is usually means it'll show up as the last one on an example on a final exam, right? If I was to use this question for a final exam, I would probably leave that last one. That's how you separate the A students from the B students, right? By putting some questions that are more difficult than others. That's it. And that's a trick of writing the final exams, is you write the final exam where the average student who's paid attention is going to pass the exam with a C. The one who's a little bit better than average is going to end up with a B in it. And those who really understand it should end up with an A. So that's the way this homework problem is written right here, is that any goofball should be able to solve that one, right? Anybody that was half awake during class should be able to figure that one out. This one's a little easier or a little harder, but not too bad. You get into these last two this one the B student should be able to figure out. It's going to be the A student that figures that one out. By the time you go through all the tricks and all the steps that's the more difficult problem on this particular problem right there. So you got 5 parts to them, but they're not all 5 equally difficult. And as you can see, that last one, involved quite a bit to get down to the right answer. That's there. Because I also did mention the other one is going to be A naught plus A B naught. That one right there. When you look at that one, that's equal to A naught plus B naught right there. So you've got 4 versions of that rule right there. That rule expands, and you can go through and derive each one of those 4 versions by by using replacements. That's there. In other words, I said C is equal to A naught right there, and then I could say D is equal to B naught. And if I write this expression that way, it's going to look like C plus C naught D right there, and that looks exactly like the original one right here. See, this is in the same form of that right there. Because I replaced A naught with C and B naught with D, if I went back and replaced them back again, I end up with this statement right there. So again, that goes back to the understanding of that there. And while I'm off on the tangent here, I should point out the difference between an engineering student and a technology student is that the engineering student should be able to see these things as they solve these problems. It's not obvious that this is uses the same rule as that there. It's not obvious. But by going through this substitution, it's where you would find that it is the same rule right there. So, how am I on time? I got enough time to go through another one. Usually I set it about an hour and 15 minutes where I like to stick these things. I know that breaks the rules of 2 hours, but 2 hours is too long. That's it. And actually, what I've kind of discovered is I probably cover as much material in 75 minutes, and some instructors probably do in 2 hours. That's there. I try not to get off on tangents too much. That's there. So, okay, let's look at the next homework problem. Right there. And sorry for flipping through the book, but I just find it easier to use the book than it is to try to follow the PowerPoint slides. Right there. So, and what I've also discovered is that when I use the PowerPoint slides, I've found that too many students expect the exams to come out of the PowerPoint slides only. No. The PowerPoint slides are just a guide. That's it. Now, we're going to come back and cover the rest of this chapter as we move along. Now, the next set of problems here require the use of something called De Morgan's rule. Right here. Right there. Identify again, as we go through here on the next section right here, simplification, that there, we've got 5 here. I don't know if I'm going to go through all 5 of these, but we'll go through some of them here. But let me, again, cheat and cut this and put it on the OneNote. Right there. And you can see how easy it is to steal questions out of the book, though, for exam questions and quiz questions. I actually had a professor when I was an undergraduate tell us, and early on, that he was going to, well, you zoom in. Okay, we'll just go ahead and do it this way right here. So let's use Boolean algebra. Let's just go through and select here. And I'm going to go through probably the first 3, but we might actually, let me do C and E for right now, okay? Let me do C and E, because that one's fairly interesting, because C is AB plus AB naught plus A right there. AB naught, I didn't write this here right. This is AB naught C right there. And what I'm going to do to that there is I'm going to combine the first 2. And the first 2, when I combine those, is going to be right there, C times A B plus A B naught right there. Yeah, no, I can't combine the first 2. What am I doing here? I'm right there. Well, actually, yeah, that there, this is C right there. I guess I do have to go through and expand them right there. So what I'm going to do is I'm going to expand this one right here. So this is going to be AB plus A naught plus B naught right there times C plus A right there. So now I'm going to go ahead and write this one out, and it's going to be AB, that's not a not there, that's me, that there, plus A naught C plus B naught C plus A right there. Now, when I look at this one right here, first off, I can combine the first 2 and make that term disappear. Right there. So, in other words, A 1 plus B, right there, see that? Plus A naught C plus B naught C, right there. This disappears, right? So now we're left with A plus A naught C plus B naught C. Now, if we look at this 2 right there, that's that form that we just looked at, right? That's the same as the previous slide, right there. So this becomes A plus C, right? That, you know, that uses that one that I said is very handy, but driving it, you know, that I had 4 versions of it. That's that same form. So when I do that, that's going to be equal to A plus C plus B naught C right there. Now when I look at these and I factor out a C, that's equal to A plus C 1 plus B naught equals A plus C, right there. As you can see, I grabbed number C. It wasn't the easiest one, but you can see all the tricks that you have to use to apply these here. Right there. So I said I was going to do that one, and what was the other one I was going to do? But you go through, as you go through it and you do it step by step, you can see how this process works of applying Boolean algebra. Now, as we go through this, keep in mind that in about another week or so, I'm going to throw Boolean algebra away and use another technique that's much easier. But you still have to know how to do this. That's there. You know. So in real life, we don't use this very often, but once in a while we do have to use that. So when I say real life, so I said I was going to do E, right? E was the other one I was going to do. And E actually turns out to be very easy. E is a little weird, because if you notice E right off the bat, you can make one of those disappear. Right there, they're repeated. Right there. So I'm going to repaste that just simply so that I don't have to keep going back and forth. Right there. And I'm going to look at E. E is AB plus A naught plus B, or plus B naught, times C plus AB. Now, first thing I'm going to do is look at this and realize that AB plus AB plus A naught plus B naught times C is equal to, one of these can disappear. That comes back to A plus A is equal to 1. That's the rule. See, and I just moved this over to the front there. So that is going to be equal to AB plus A naught plus B naught, there's a naught there, C, right? Now I'm going to rewrite this using De Morgan's rule, and that's going to be AB plus AB naught, right there, applying De Morgan's rule, times C. Now I'm going to factor this, and that's equal to C AB plus AB naught. Again, I'm treating this as a single term, and that's going to be equal to 1. So this whole thing reduces down to C. But you can see it's one of these things that, and you know, I'm going through and doing this, and I've got decades of experience doing these problems every time I teach this class. Now, I'll be honest, I haven't taught this particular class in probably 10 years because I've been teaching the advanced course. That's there. So in the advanced course, I don't go through this, but I did teach this course for at least 10 years or more, off and on. So I've gone through this many times. I don't expect that you can look at these and see them as quickly as I do. It's the tricks. But again, that's one of that there. And as I said, I was going to go through a couple of examples to kind of show how it's done that there. So, any questions? We're going to come back and we're going to probably do a few more just to review this on. And we said we meet on Tuesday, right? Yeah, next Tuesday. And then I'm going to get into some other terminology. And then probably by next Thursday we'll get into Karnoff maps. And then after that, I probably want to schedule a lab session. I want to give a couple. Wait, next week we have Thursday, Friday off, right? Isn't Hari Raya Haji is next Thursday, so Friday's off. So next week I'll see what we're going to cover. So then probably, you know, I think I'll probably try to schedule the lab a week, 2 weeks from today. In other words, we'll go through a lecture on Tuesday, and then the following Tuesday I'll schedule a lab if I can get the room. I just want to get you in there and play with some hardware. You know, seeing ones and zeros gets boring after a while. At least turn on some LEDs and flip some switches for a change. And see that it actually does work. That's it. So, okay. And let me stop this here. Yeah, see, I'm right at the hour 15 minutes up there.